Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Wafiy Darwis bin Affandee. My metric number is 22130239. So today we will be presenting our assignment, which is the PCMs. The topic we choose is decoding the digital world, exploring pulse code modulations. So let's begin with the introductions to the PCMs. So what is pulse code modulations? So PCM, or they call as pulse code modulation, is a digital signal processing method that convert analog signals to a digital representations. So it's the most commonly used technique for encoding analog signals in digital systems. So why PCM is matter? So PCM enables reliable transmissions and storage of signal in digital communication systems. So the digital representation is less prone to degradations, ensuring higher fidelity over a long distance. So let's take a bit look into the extra informations. So the core idea of the PCM is by breaking down an analog signal into discrete time and amplitude levels. So PCM creates the digital equivalents that can be stored, processed, and transmitted efficiently. So now let's begin into the PCM techniques. So the key feature of the PCMs are divided by three: sampling, quantizations, and encoding. So for the sampling is called as discrete samplings. It captures the analog signals at uniform intervals of times. So the quantizations level is convert each sample's value into a finite set of levels. And the binary encoding, each quantized value is assigned a unique binary codes. So now let's talk about the type of the PCMs. There's three in these slides, which is the linear PCMs, or they call as LPCMs. It is the uniform quantizations level across the signal range. And the second one is differential PCMs, or they call as the DPCM. So encodes the difference between successive samples, reducing the data size. And the third one is adaptive DPCMs, or add PCMs. It adjusts quantization step size dynamically for better efficiencies. So why PCMs? So it provides a robust framework for storing and transmitting signals with high accuracies, making it the backbone of digital communications technologies. So now let's talk about the advantage and disadvantage of the PCMs, of pulse code modulations. So the advantage of the PCMs, in these slides, we have 4 for the advantage and 4 for the disadvantage. So for the first advantage is the noise resistance. Digital signals are less affected by noise and distortions during the transmissions. And the next one is the error detections and corrections. It is allow for advanced error checking method to ensure data integrity. And the third one is the storage efficiency. Digital signals can be compressed and stored without the significant quality loss. And the fourth one is scalability. Supports its higher resolutions format by increasing sampling rate and bit depth. So now let's talk about the disadvantage of the PCMs. So for the first one is the high bandwidth requirement. PCM signals occupy more bandwidth than their analog counterparts. And the complexity is the encoding and decoding requires sophisticated hardware and software. The third one is the quantization noise. So approximating continuous signals to discrete levels introduce a small amount of error. And the last one is the processing power. The high resolution PCM signals demand significant computational resource. So now let's look into the real life applications of PCMs where we can use it in our daily life. So for the first one is the telecommunications. So PCM is the foundation of digital telephony systems, including ISDN, DSS, and VoD. So it used in the time division multiplexing TDM to transmit multiple signals over a single channel. So next is audio storage. So PCM underpin the audio formats used in CDs, DVDs, and lossless digital audio. In high quality audio in recording studios use PCM for precise sound reproductions. So now let's look into the next one is the broadcasting. So it used in digital radio and television broadcasting systems. And the last one is the medical device. We can see the medical device used in the hospitals, which is the MRI scans, ultrasonic sounds. It enables precise signal processing in the ECG message.
Hi, Assalamualaikum. My name is Luqman Hakim by Mohd Nazir, and I will explain how does PCM works. So, firstly, PCM, as we all know, pulse code modulation or PCM is a method used to convert analog signals to a digital signal. So, PCM works through three simple steps, which is sampling, quantizing, and also encoding. Firstly, an analog signal is going through a PCM encoder, and we'll start by the first process, which is sampling. So then sampling will sample the analog signal at regular intervals by sampling. So what it will get the PM signal like here, which or PM signal or pulse amplitude modulation signal. Next up, it will go to the quantizing process where the PM signal will be measured to numerical value of sample and assign the sample signal to a predetermined discrete level. So lastly, the quantized signal will be encoding so that we will get the digital data where it converts the numerical value into binary data. So I will explain how does sampling works. Firstly, sampling is a process used to convert continuous time signal to discrete time signal. So the sufficient number of samples of signal must be taken so that the original can be represented by its sample completely, and it shall be possible to reconstruct the original signal from its sample. So just like the last slide, where we have the analog signal, when it is sample, we get the PM signal. Where each of this blue line inside the analog signal is a different amplitude. So this amplitude will be able to reconstruct the original sample back again. So for the Nyquist sampling, Fs equals to more than 2 FM, where Fs is sampling frequency and Fm is the highest frequency present in signal. So let's say if a signal is of 10 Hz, its sampling frequency must be equal to or greater than 20 Hz so that it can be represented by its samples completely. So next step is quantization. So what is quantization? Quantization is a process of assigning the analog signal samples to a predetermined discrete level. It is also called the process of rounding off a sample according to the sum rule. For example, 4.378, we can simply round off to 4.4, and other one is 0.002 where we can round off to 0. So from the PM signal, from the sampling process where we quantize it, we will get the predetermined discrete level, just like this figure. So it can also be described as L to the power L equals to the power of n, or n equals to log base 2 L. So there are two types of quantization. The first one being uniform type, where the uniform type is a level of the quantized amplitude are uniformly spaced, and the other one is non-uniform type, where the levels are not uniform. So in these two different figures, we have uniform quantization where the line of amplitude discrete levels are equally uniform, while the other one non-uniform quantization, it is not uniform. So where we can see it has the largest step size and also the smallest step size. So there are two types of uniform quantization. The first one is mid-thread, which is the origin lies in the middle of a thread of the staircase. As we can see in the red circle here, it lies on the X level. So it is more utilized for odd levels, and the other one for uniform quantization is mid-rise. where the origin lies in the middle of a rising of the staircase. So as you can see here, it more represents on the y-axis. So it is utilized for even levels.
Hello and Assalamualaikum. My name is Murtadza bin Ahmad Azmi and big number is 2213026. And I'm going to present about encoding under pulse code modulation PCM. So this is my part number 9, encoding. I'm going to explain what does encoding means. I'm going to show the steps in PCM encoding. I'm also going to show the examples of encoding. Encoding under pulse code modulation. So what does encoding means? In pulse code modulation (PCM), encoding is the process of converting the quantized analog signal into a digital format binary code. It is a crucial step that follows quantization and ensures that the signal is represented in a form suitable for digital transmission or storage. So here are some of the pictures. So this is the discrete levels to the sampled values in order to convert the quantized levels to binary. So here you can see there are around 7 sampled values. So in order to change to binary coded decimal to form a digital output signal, you just have to do it in order from left to right. So the first one is 111, 111. So digital output signal will also be 111, 111, and then 001, 210, 011, and then back to 111, and let's say 011. So I'm going to show the steps in PCM encoding. So the first one is the input, which is the quantized signal. After the quantization step, the continuous amplitude values of the sample signal are replaced with discrete levels. I'm going to show you. So from analog signal, continuous signal become discrete time signal. This is the discrete time signal. You can see the discrete levels 1, 2, 3, 4, 5, 6, something like that. So for example, if the quantized signal has 16 discrete levels, those levels can be represented by numbers from 0 to 15. So this is what I mean. So if there are 16 discrete levels, it will be represented by numbers from 0 to 15. So there are 16 discrete levels. So binary representation. Each quantized level is assigned a unique binary code. The number of bits required depends on the number of quantization levels. So the formula is n equal to log base 2 of L, where L is the number of levels. For examples, if there are 8 levels, which means L is equal to 8, which the formula will be n equal to log base 2 of 8, equal to 3 bits are required, because in order to get 8, 2 to the power of 3 will be 8. So 3 bits are required. If the quantized value is 5, its binary representation in 3 bits would be 101. So from decimal value, in order to change to binary value, binary coded decimal, under 3 bits, the decimal value of 5 will be 101 in binary coded decimals. So that's what it meant. And the next step is mapping quantized values to binary codes. Each quantized value is converted into its corresponding binary representation. This creates a sequence of binary numbers that represent the original analog signal. So I'm going to show you the example. So I got this from the slide of chapter 4 part 2, PCM encoding examples. So here you can see there is a table. Levels are encoded using this table. So level 0 until 7, and this is the code word from 00 until 111. So what does it mean? So level means in decimal value form. The code word means in binary coded decimal, BCD. So in order to convert from decimal to binary, you need to know for decimal level 0, in binary code word it will be 000. For 1 it will be 001, and until 7 it will be 111. So this is the quantization levels with belonging code words. So here we can see chart 1. Chart 1 is the quantization and digitalization of a signal. Signal is quantized in 11 time points and 8 quantization segments. So 8 quantization segments is equal to 8 quantization levels. As you can see here, 0 until 7. That means there are 8 quantization segments. 1, 2, 3, 4, 5, 6, 7, 8. It will be 8 quantization segments. And 11 time points means 11 sampled values for these discrete signals. 5, 7, 6, 1, 2, 4, 7, 4, 3, 2, 5. So in order to change it to binary coded decimals, or in encoding process, here you can see in chart 2, process of restoring a signal. PCM encoded signal in binary form. So in encoding signal in binary form, it will be 5 will be, you can refer to the table. Level 5 encode word is 101. So in binary form, it will be 101. We need to do this in order from left to right. So 5, 7, 6, 3, 4, 5, 7, 6, my bad. 5, 7, 6, 1, 2, 4, 7, 4, 3, 2, 5. So in binary, for each of the sampled values will be 101, 111. We just put it and refer it to the tables. So total of 33 bits were used to encode a signal. So that's the example. So let's go back. I'm going to talk about the output digital signal in order to explain it a little better. So the encoded binary sequence is now ready for transmission or storage. Example, a quantized signal with levels 3751 is encoded as 011, 111, 101, 001 in binary. Hello and Assalamualaikum. My name is Murtadza bin Azmi and I'm going to show you pulse code modulation PCM simulation using multi-sim. So I derived this, I got this from Lab 4, which I have done before this, Lab 4 under communication system. So I'm not going to explain the circuit much. I'm just going to explain the waveform on the 4-channel oscilloscope. So I'm going to explain which is the sampling process, which is the original analog signal, the quantization process, and the encoding process. So as we can see here, there are 4 types of waveforms. The first one is the blue waveform. This is the sampling signal, as it appears as a square wave. Sampling involves taking periodic samples of the analog signal, and the square wave here represents the sampling clock signal that triggers the sampling process. And the second waveform is the input signal. I'm sorry that I didn't put this in order, so that's why I will explain it. So the second waveform is the original analog signal that is being processed. It represents the continuous input signal that is sampled, quantized, and encoded. And the third waveform, as you can see here, the orange waveform, this is the digital output, meaning the encoded signal, as it consists of high frequency digital pulses binary data. It represents the final PCM output where each quantized levels is encoded into a binary representation. So why this is the encoded signal mean in binary form? Because in binary form there's only 1 and 0. So you can see here the highest amplitude is the 1 and the lowest amplitude is the 0. So this is confirmed as the encoded signal. The last signal is the pink waveform. This is the quantized signal as it appears to have a staircase-like pattern. Quantization converts the sampled values into discrete levels, which is visually represented by the step-like changes. So that's all from us. The representation of PCM. That's all. Thank you.